Hello and welcome. We're going to do this problem today, unique paths problem. So here is the problem set. There was a robot in an n by n grid. The robot is initially located at the top left corner at grid 0, 0. The robot tries to move to the bottom right corner. The robot can only move. So hello and welcome. We're going to do the unique paths problem today. So and we're going to use the UMPIRE method to solve it. So the problem is this: there is a robot on an n by n grid. The robot is initially located at the top left corner. The robot tries to move to the bottom right corner. The robot can only move either down or right at any point in time. Given the two integers m and n, return the number of possible unique paths the robot can take to reach the bottom right corner. And the test cases are generated so the answer will be less than or equal to 2 times 10 to the 9. So to get a better understanding of what's going on here, we have this robot right here, and we have this finish line right here. And we want to take this robot to go through a sequence of right and downward steps to get to the finish line. And so what do we understand here? So we want to get an understanding of inputs. The input is non-positive integers, m and n, and the output is the number of unique paths the robot can take on an n by n grid. Okay, so if you want to understand the examples here, say if we have a 3 by 7, so there's 3 by 7, we're 1, 2, 3, 4, 5, 6, 7. So this is 3 by 7 grid, for example, and we want to count the number of unique paths, so we would go right, 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 and then down, down. And that's one path. And then we go down, down, right, 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 right. And that's another path. And so we can also do these kinds of combinations of paths there. So where we continually go right or down to get to the finish line. And if we count all the possible combinations of right and down, we'll see that the output is actually 28. And similarly, if we have an M3 by 2, if we count the 3 by 2 here, this grid right here, we can see that there's one path, there's two paths, and there's three paths. So from the top left corner, there are a total of 3 ways that to reach the bottom right corner. So you can go right, down, 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 right, or down, right, down. So that's it. So that's a good understanding of what's going on here. So we can go to the next step, which is the match. So match is similar problems are like search or combination, using combination to search for uniqueness of paths, and also some kind of algorithm problems, and factorial we'll have to use as well. So to the next step is to check out what the plan is. So we want to understand how to implement this. So first, we want to set up an algorithm to compute this number of unique paths. So what we can do is we can notice that we have m minus 1 downward moves that we have to make. So m minus 1, right? So this is 3, and then we have downward. We have to go down twice, and there are going down, and n minus 1 going right. So we're going right and minus 1 times 1, 2, 3, 4, 5, 6, 7, or up to 6 here. So we can take a combination of n minus 1 plus n minus 1 moves and choose n minus 1 of those to be down or to be right. Or in other words, we can rephrase this as let's choosing n minus 1 to be down. So what is that? That's basically the combination. That's computing the combination. M plus n minus 2 combination n minus 1. And that's equal to m plus n minus 2 divided by n minus 1 factorial, or n plus n minus 2 factorial, divided by n minus 1 factorial, and that multiplied by n minus 1 factorial. If you compute the formula for combination here, you'll get n minus 1 for the last factor. And so what we can do here is so this gives us total unique paths. So what we can do here is we could just write a function that computes this combination. Okay, so we're just going to go right ahead and implement this. So what we're going to do is 1, 2, 3, 4. Yeah, I'm just going to write the implementation up here. So the implementation is we want a factorial. So we start with the factorial equals 1. And we want to range I for I in range from n to m plus m minus 1. So if you calculate this, we can just subtract off the n minus 1 factorial. So we can start with the nth element in the m plus n minus 2 factorial. And that's where we start with where the range is equal to n. And then we can go all the way up to n plus n minus 2, which is n plus m minus 1, that range capped off. And so then we want to divide by m minus 1 factorial. So we have a factorial that is multiplying by each factor of I, and then dividing by this n minus 1 factorial, which is I minus n plus 1. And so we have that, and then we can return the factorial, and we're done. So we'll run the code. So we got this solution accepted, and then we can run for all submissions. Okay, so we got a pass on that. So this is a correct solution. So now we can go through a review of this solution in Python 2 code. So we just iterate through this, and we go with the inputs. The input is 3 and 3, and we print out this unique pass function, and it goes through the factorial. So it just iterates over the factorial to compute the combination. And then when it's done, we get 6. And that's the answer for this solution when we have an input of 3 and 3. So that's a short review of this function. Now we can evaluate this function. So an evaluation is that the time complexity is going to be O of max mn. It's just iterating over this one range over here. And the space complexity is going to be O of 1 because we don't use an array to save any values that vary with input size. So we have O1 space complexity. So that's about it, and that caps up our explanation for this problem, unique paths. Thank you for listening.